Welcome to section 10.5, Angles of a Circle. Today we're looking at the relationship between the angles formed in a circle and then the arcs that they intercept. We have three different basic types of angles, and it has to do with where the vertex is located. So the vertex, again, is where the two rays meet to form the angle, the corner of the angle, if you will. So the first type is when the vertex is on the circle. And if you have a vertex that's on the circle, you're going to take half of the intercepted arc. So looking at the two different types of intercepted or vertex on the circle that we have an inscribed angle. So the inscribed angle is when the vertex is on the circle and it's made of chords. And we have a tangent chord angle composed of a tangent, segment BC, and a chord, segment AB. In either case, when the vertex is on the circle, you take half of the arc, and that will give you the measure of the angle. Similarly, if you know the angle and you want the arc that it cuts off, you're going to double that. So looking at our diagram that we have here we go. We got a little investigation that we can do. We have a tangent chord angle, and you'll notice that right here we have our pink angle, or pink arc, and it's going to cut off an angle here that's the tangent chord angle. So looking at the relationship between that angle, it's 64.13 degrees. The arc is 128.26, again twice as big. And it's the same on the other side with this green angle, this green arc. The angle is 115.87. The arc is double that, 231.74. Now I can drag these points and I can move it around, and the relationship is still there. 75.09 doubled gives me 150.18. The arc is 150.18. The angle is half of that. And same on the green side. Again, I can keep moving that around, and the relationship is maintained. The tangent chord angle is half as big as the arc that it cuts off. The second type of angle-arc relationship we have is when the vertex is in the inside of the circle. Now there's two types, and the process that we follow is a little bit different for each one. The first type is called a central angle. We've already talked about that. The central angle is an angle where the vertex is at the center. And the measure of that angle is exactly the same as the minor arc. But with a chord-chord angle, it's a little bit different, because now our vertex is not at the center. It's somewhere to the left or to the right or above or below. It's not in the center, but it's kind of near it. To solve a chord-chord angle, we have to figure out which arcs are across from each other. So looking at our diagram that we have here, we see that arc AD and arc BC are across from each other. If I add those up and divide by 2, so average them, that's going to give me my chord-chord angle. Now we know that these two angles right here, angle AED and angle BEC, have to be congruent because they're vertical angles. So using a similar reasoning here, we can say that angle BEC is going to be arc AD plus arc BC divided by 2. Now we have a diagram for this one as well. Get to the right file. There we go. So for this one, we're again investigating what happens when we have the chords, what happens with the angles that are formed by that, and what's the relationship between the arc that is formed by those chords. Once this loads up, we'll take a look at that relationship. There we go. So again, we have these pinkish purple arcs, I guess we'll call them magenta, and then we have these green arcs right here. So looking at this circle down here, this is telling us exactly what those measurements are, what the arc is and what the other arcs are as well. I can move that around, and you'll notice that when I'm changing that arc, the angle's changing as well. So here I have a 59.12 degree angle, or arc I should say, and a 68.35 degree arc. If I average those out, I end up getting this chord-chord angle, which is 63.73. Do the same thing for the green part, 176.59, almost a semicircle, pretty close, and then 55.95. I average those out and I get about 116. So again, moving those arcs around doesn't change that relationship. I can move this angle too. I can move this, and it's still going to be the relationship that the two arcs across from each other added up and divided by 2 averaged are going to give me my chord angle. And then the last type, and there's only two drawn on here, but there's actually a third type, and we'll discuss that real briefly. But it's when the vertex is outside the circle. And in this case, instead of adding up the arcs and dividing by 2, you're going to subtract them and divide by 2. And it's important that you go from the bigger arc minus the smaller arc. Otherwise, you're going to get a negative measurement for our angles, and that just isn't going to happen. So the first type is called a secant-secant angle, and it's made of two secant segments. Secant segments, just to refresh your memory, connect 2 points on a circle, and they're going to keep going to the outside. Now they intersect at point C, which is where the vertex is. It's outside the circle. So I take my arc, here we go. I take my arc AE and my arc BD, I subtract them, multiply by 1/2, and that'll give me my secant-secant angle. I do the same thing for the secant-tangent angle. I take AD minus DB, multiply by 1/2, and that gives me my secant-tangent angle, which again, the vertex is outside the circle, so that's the measurement that I'm looking for. And the third type, we've got another one called the tangent-tangent angle. It's the same basic idea, but it's made of two tangent segments instead of a secant or a tangent. So looking at our next file for this, we're going to investigate the secant-secant relationship and see if we can verify that that actually works. So here we have a secant segment, segment EC, and another one segment DC. Again, they both intersect outside the circle at point C. I can move this around. I can move this around as well. I do anything I really want with those points and change it around. You notice that when these arcs get smaller, that angle gets smaller as well. Because again, I'm subtracting those arcs off and I'm dividing by 2. So 101.51 minus 38 divided by 2, that gives me about 31.7. If I double that, that would be about 63, which is 101 minus 38. And I can make the arcs bigger, and when I do that, my secant-secant angle is going to get bigger as well. So that relationship is still there. 147.5, take away 56.24, divide that by 2, it gives me 45.63. So let's do some quick examples. How does this work? How do we apply this? We want to find the missing angle measurements. So in this case, for this problem, this is a chord angle because we have two chords that are intersecting on the inside of the shape. My two opposite arcs are these guys right here, 123 and 55. So if I want to find the measurement of angle FHG, it's 1/2 of 123 plus 55. So I'm going to add those up. I'm going to take 123 plus 55, and I'm going to get 178. And when I divide by 2, I get 89 degrees for the measurement of angle FHG. Similarly, EHS is the same exact thing. They measure the same. Example number 2. We have a secant-secant angle. Again, the naming of it's not as important as where's the vertex. The vertex is outside, so if the vertex is outside, it tells me I have to subtract my two arcs and multiply by 1/2. So the measurement of angle U, and I can call it U because there's only one angle U there, it's going to be 1/2 of 160 minus 60. That's 100. Take half, you get 50. In our last example, we have a tangent chord angle. ML is a tangent, LK is a chord. And what we want to do is figure out what the measurement of this angle is. Again, the vertex is on the circle, so all you need to do to find the measure of angle MLK is take 1/2 of the arc that's cut off. 1/2 of 100 is 50. So again, the main idea for today is make sure that you know exactly where the vertex is. If the vertex is outside the circle, you subtract, divide by 2. If it's inside